Okay, so let's continue then. We're in the business of detecting errors, and to our help we have these binary codes. And we saw that the error detecting block here, the only thing it does in principle is to look at the receive pattern and say and inspect that and say if it's a code word, it will accept it. If it's not a code word, it will say an error has occurred. That's the whole thing. The rest is implementation. And when we have systematic codes, the implementation is quite easy. The only thing we do is we take the corresponding data field of the received word, we compute the parity bits that belong to that bit pattern, and compare that to the parity bits we have in the received word. If those happens to be the same, then the received word is a code word, and we say it's no errors have occurred. If the parity bits are different, we know that errors have occurred, and then we say so. Okay. Now, we can make an error in this. The error detection could be wrong. Okay. And it can be wrong that it can accept a code, it can accept a pattern Y, which is not equal to the transmitted code word. Okay. And it can do that when the received word is a code word, but not the same code word as was transmitted. So in mathematics, this means that error detection will fail if we have a non-zero error pattern E. Okay, so this is not all zeros. That when we add E to the data that we transmitted, we get a code word. Okay. So that code word is not the same code word as we transmitted, but we will accept it, and yeah, bad things happen. So this is an error event which is when the error pattern is like this, we say that the error pattern is undetectable. Okay, we have no way of detecting it, and it will cause problems later on. So this is something that we really would like to avoid. Okay, because otherwise we will pass along some erroneous data, and then maybe an application will crash or something like that. So that's not so good. Okay, so it can be shown for this particular code, we can actually list the error patterns which are undetectable. So for our example, the undetectable error patterns are, and here it's actually an interesting exercise in trying to figure out what the error patterns are. If we look at this code here, if I flip just one bit position in the code word, we see that the resulting pattern is not a code word. Okay, so it will detect all single error patterns here. And for simplicity, let's assume that we transmit the all zero word. If one error occurs, then one of these positions will flip its polarity and become a 1. And you see that there is no such code words down here. Okay, so an error can occur here, 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 or here. All of these will be detected. Now, if there are two errors that occur in the code word, if they happens to be here in these two positions, then we will detect that error pattern because there is no code word which is 1100. Okay? If the two bit patterns, bit errors happens to be in the last two bits, the same thing, we'll be able to detect those. If it's in the first and the third position, we will be able to detect that. But not if it's in the first and in the last. Okay? Because we have 1001 is a valid code word. Right? If we transmit this, we flip the first and the last position, we get this code word at the receive pattern, and the error detection circuit will say, great, no errors. So that's an undetectable error pattern, right? So one error pattern which is undetectable is the 1001 pattern, right? And we can see that that actually is true for this pattern also, right? If we flip this one and that one, we get this code word. So it's not only the all zero code word which have problems with this pattern. Same reasoning, we can see that this one is also undetectable when we flip the two middle bits. And there is one more pattern. Which one is that? See it? The all ones, right? This pattern will not be detected either, right? Take the all zero word, flip all the bits, you get another code word. And you can do that for all the, you can check that that is true for all other ones too, right? So, if we're unlucky, nature is going to cause these type of error patterns, and then we have no way of avoiding making erroneous error detection. So what one would do, ideally, when constructing codes here, is to make sure that these error patterns are as few as possible, but even more important, that they occur with the smallest probability possible. Okay, and one can almost understand what we would like to make sure is that these error patterns here have a lots of ones in them, because to have a lot of errors in a row is quite unlikely compared to having just one error, for instance. Or an error pattern with just one error is more likely than one with two. You agree? Right? Because error occurs, hopefully, not so often, right? So let's, we should formalize this a little bit, but that's basically what we're looking for. We're looking for codes where the undetectable error patterns are unlikely to happen. Then we will have not so big problems with this. Okay, and to figure this one out, we need to make a little bit of detour into the math to make these ideas a little bit more rigorous. And let's start with introducing called Hamming weights. So Hamming weights works on vectors, and it counts the number of ones in a binary vector. So that's the Hamming weight. So the Hamming weight for this pattern here is 2. This one also Hamming weight 2. This one has Hamming weight 4. Right? So I just count the number of ones in the pattern. Okay? So that's the Hamming weight. And it's a distance metric in the sense that it measures length of binary vectors. So the Hamming distance between two binary vectors is the number of positions in where they differ. Okay? So the Hamming weight, the Hamming distance between u and v and the two binary vectors is the number of bit positions in which u and v differ. I should say differ here also. Okay, so the Hamming distance between this and this pattern happens to be, what's the Hamming distance between these two? Four, exactly. They differ in all positions, so 4. Hamming distance between these two? 2, exactly. They differ here and here. Okay, so this Hamming distance is quite useful because now we can measure closeness between binary vectors in a very easy way to do that. Right? We just count the number of positions where they differ. And if you like, what we can do is we can just take the modulo 2 addition of u and v, okay, and then count the number of ones in that addition. Now I made a mistake in the modulo 2 table later on, so this is the correct one. So 0, 0 gets 0, 0, 1, 1, 0 gets 1, 0, 1 gets 1, and 1, 1 gets 0. So when we take two binary vectors and we add them modulo 2 to each other, it will be a vector where there are ones in those positions where the two different vectors have different bits. Okay, 0, 1, or 1, 0 gives 1 at the output. Okay? So these Hamming distances are quite useful, as we will see. So suppose we have a code with 4 code words here. They're placed out in some space, binary space. And then we can calculate something called the minimum distance. And the minimum distance is the smallest Hamming distance between any pair of 2 code words. So what we can do, so mathematically it means that the minimum distance is the minimum of the Hamming distance between the kth and lth vector, as long as k is not equal to l, right? And these are members of the code. So here we have 4 vectors. We haven't specified their dimension. They could be 128-bit long vectors if they are, but there are only 4 of them. Okay. So what we want to do then is measure the Hamming distance between all of them until we find the smallest one, and that we call the minimum distance. And that happens to be this one. Okay. So why is this useful? One, it's because when we transmit C2, for instance, there might be an error occurring on the channel, and then the received pattern will be the transmitted vector plus the error. It would end up here. And then the question is this error detectable or not? Is this a detectable error? Yes, it is. Why is that? It's because Y is not a code word, right? It's not C3, C1, C4, or C2. Okay? So this is a correctable error pattern. Can you see the implication of the minimum distance and the error pattern? We say that E is detectable. Okay, that is the same to say that the output Y, which is C plus the error pattern, is not a code word. Okay, so that if E is detectable if and only if this is true, right? That is that we take the transmitted code word and add it to the error pattern, and then we get a Y. That should not be a code word. Then we are able to detect this error. Okay, and this should be true for all starting transmitted vectors. So if we look at Y here, we see that regardless, if we look at E, regardless to which C we add it, we're not going to end up on another code word. Okay, so this is a detectable error pattern. What we can do then is we can draw these spheres with radius minimum distance around all code words. And then we know that as long as the error does not go outside this sphere, or even touch it, it cannot even touch it. But if it's inside the sphere, then we can never reach another code word. Right? Because the minimum distance is the radius of the sphere. And if the error has a Hamming weight, which is less than the minimum distance, we can never go to another code word. You see this? If the length of the error is too small, it can never reach another code word. Okay? And we can guarantee that if the length of the error pattern is less than the minimum distance, we can never reach a code word. So, if the Hamming weight of the error pattern is less than the minimum distance, then we know for sure that E is detectable. Okay. So, what is the minimum distance for this code? 2. You see that, right? So whenever I go from one code to another, I need to flip at least 2 positions. Okay? So the minimum distance for this one is 2. So we know for sure that all 1-bit error patterns are detectable, right? Because they have Hamming weight 1, which is less than the minimum distance for this code. Okay, so we can easily, with looking at the code words and figuring out the minimum distance, we can say already something about what patterns are guaranteed to be detectable or not. So, I mean, a good code then, should it have a large or a small minimum distance? Large, exactly. We want that sphere to be large, right? Because then it covers a lot of error patterns, and a lot of error patterns is then detectable. Okay. So we want codes with large minimum distance. Now, so this that the weight of the error pattern is less than the minimum distance implicates that E is detectable. Can we turn this around? No, we cannot. So if the Hamming distance of the error is larger or equal to the minimum distance, we're not sure if it's detectable or not. It could, but it could not be the case that it's detectable. Okay? And why is that? Well, it's because an error pattern not only has to have the right length, it needs also to point in the right direction in order to reach another code word. So for instance, this error is undetectable. That is, if we transmit C3 and the error pattern EUD occurs, then we end up at C2 and we will not be able to detect that error. And we see that this error happens to be have exactly Hamming weight minimum equal to the minimum distance. Now this error pattern, however, is, first of all, it's longer than the minimum distance, but it's pointing in the wrong direction, or right direction. It depends on how you look at it. But for sure, if we transmit C4 and we receive Y here, we would find that error, right? Because Y is not a code word. The only thing we have problems with is that when we go from one code word to another code word, and these specific error patterns are the problematic ones then. Okay. And we see in general that there might not be very many of those. In this case, there were only 3 patterns out of 16 possible. So we were able to, out of 16 possible error patterns, one is the all 0 error pattern. That's no error at all. So there are 15 error patterns that are non-zero. Out of those, we can detect all but 3 in this case. Right? Okay. A small detour into error correction also. So we can actually also detect and correct a few errors without asking for retransmission. If we can identify those bit positions that are suspect somehow, right? And the way to do that is that we still have the minimum distance, we still have the same code, and then we have an error pattern that looks something like this. Now, what we could do is that we could correct errors also. And the way to correct errors is that if the received word is closer to C2 than to any other code word, we can basically decode to C2. Okay? By looking at Y, we can find the closest code word, and we say, okay, that's the transmitted code word. That's error correction. And an error is correctable if we do the correct decision. Okay? And when do we do correct decision? Well, we do correct decision if this is actually C2 was actually the transmitted code word in this case. Okay? So the Hamming distance between the received word, which is the transmitted word plus the error, to the transmitted code word, if that is less than the distance between the received word and any other code word, then we make a correct decision. Okay, so I'll take that again, right? So what we do here is that given Y, we decode to the closest code word. Okay? We make a correct one if the closest code word is what was actually transmitted. Okay? And that is guaranteed if the distance to the transmitted code word is less than the distance to any other code word. All right. So what do that have to do with minimum distance? Well, it's like this. If we around each code word make a sphere whose radius is half the minimum distance. Now, suppose we do that, then all of these spheres are non-overlapping. You agree? They cannot be overlapping. There are some which are touching here, And those are touching when the corresponding code words are on the minimum distance. All other code words are at the longer distance. So if we think of this as we have our code words, and then we put a lot of oranges around those, footballs if you like, with a certain radius, then all error patterns which are such that they are confined to that sphere will be decoded to the right code word. If we transmit C2 and the error is such that we never go outside this sphere, then when we decode to the closest code word, we will decode to C2. Same thing. If we transmit C4 and the error pattern is such that it belongs to the decoding sphere here, it will be decoded to C4. And the same holds for all code words here. So, if the Hamming weight of the error is less than half the minimum distance, then we can correct the error, for sure. Again, if the Hamming weight is a little bit larger than half or equal to or larger than half the minimum distance, then we're not sure. It could be correctable, but it could also be maybe not. So the minimum distance here tells us something about the error correcting capability of the code and the error detecting capability of the code. So therefore, the minimum distance is a very important parameter of a code. Okay, questions? Okay. So, basically what we're looking for when we're looking for designing of a good code for error detection or correction is that we want to find a code with a large minimum distance. Okay? And we want to do that with as high of a rate as possible. So we don't want n here to be very large compared to k, because then we have to spend many resources in order to transmit the code word, right? So we want to make the length here relatively small, okay, but still maintain a large minimum distance. So this is the role of finding good error detecting or correcting codes. Okay, and the reason why we're interested also in minimum distance is that if we look at the probability that these error patterns occur, error patterns with low weight, with few ones in them, are more probable than high weight error patterns. And we will make this notion explicit right now. So, suppose that errors that go over the channel occur independent of each other. Okay, so what do I mean by that? It means that we can think of it that we transmit bit by bit over the channel, and whether there is an error in a specific bit does not affect the probability that the next bit will be an error and so forth. So they're completely independent of each other. So the probability then of that the error pattern on the channel is equal to some binary pattern u. What is that? Well, then we just have to count. Okay, so what does this mean? Let's go this. So this is the probability that E1 is equal to U1. Sorry, E0 is equal to U0. So that's the first bit in E is equal to the first bit in U. and that the second bit in E is equal to the second bit of U. So E1 is equal, E1 is equal to U1. And then we just continue to the last bit, which is n minus 1 is equal to un minus 1. Okay, so we would like to calculate what is the probability that the error pattern E equals the error pattern U occurs. Okay, so E is the random bit error pattern, and what is the probability that is equal to U? Now, if they occur independent of each other, then the probability of this joint event is the product of the individual probabilities. So we can write this as the probability that E0 is equal to U0 times the probability that E1 is equal to U1, and then we keep on going until the last probability, which is that En minus 1 is equal to Un minus 1. Okay. So suppose now that the probability that we make an error is equal to P, and the probability that we don't make an error is 1 minus P. So P is the probability that an error is equal to 1. So the jth position is equal to 1. So this is the bit error probability. Okay, so suppose we know this. How can we calculate this? Well, the first thing we have to figure out is that if the probability of bit error is equal to P, then 1 minus P is the probability that there is no error. That Ej is equal to 0. Okay, so what we essentially want to do then is to look at this. For each time U happens to be 1, then we replace that probability with P. Whenever U is equal to 0, we replace that with 1 minus P. Right? There are only two probabilities. There are only two probabilities here because U is a binary variable, so it's either 0 or 1. 0 means no error, 1 means an error. Okay. So we see that this can be written then as P times raised to the power which is equal to the number of ones in the U vector. Right? So for each element where U is equal to 1, we get 1P. So this can be written then as the P to the raised of the Hamming weight of U. Because here's how many ones there is in the U pattern. Okay, and then for the rest, we get 1 minus P. We have the total number of element, which is n, and then we subtract off the Hamming weight of U. N minus the Hamming weight of U is the number of positions where there is a 0 in U. Right? We have n positions in the U vector. The Hamming weight of U is the number of ones, and therefore the number of zeros is n minus the Hamming weight. Okay. So here is an expression for the probability of that the error pattern takes on one specific vector U, one specific error pattern. Okay. Questions so far? Okay. So now we know how to calculate the probability that the error pattern is a certain u. Okay. How many u's are there? There are 2 to the power of n of those, so that could be quite substantial. But many of those have exactly the same probability of occurring, because we see that the probability that we take on one specific u only has to do with the number of ones in the u, right? So any pattern with the same number of ones, that is the same Hamming weight, will have exactly the same probability of occurring. You see this? Right? The probability that the error pattern is one particular pattern is given by this probability. At the end of the day, the probability only depends on the Hamming weight of u, not the specific way that the ones in the u vector is distributed. Okay? So, for example, the probability that the error is equal to 0, 1, 1, 0 is equal to the probability that the error is equal to any other 2 1-bit pattern, right? So it could be 1, 1, 0, 0. It doesn't matter. Okay. So, what is then the probability that the Hamming weight of the error is equal to some number L? Okay. So this is the probability that the error pattern has exactly L ones in it. Well, we know that the probability for one such event is what? It's p to the power of e, the Hamming weight of e, plus 1 minus p n minus the Hamming weight of e. Okay. Now this happens to be p to what? L times 1 minus p n minus L. Okay. So that's the probability for that an error pattern, a specific error pattern with L ones occur. Now how many such error patterns are there? So we saw here we had many error patterns with 2 bits in them. So in general, if we have n bits, and we need to select how many error patterns, if we have an n-bit pattern, how many of those have exactly L bits in them, L ones in them? N choose L of these, right? Where n choose L is the n factorial n minus L factorial L factorial. It's the binomial coefficient, right? So for instance, if we have 4-bit patterns here, let's go 3-bit patterns here. Okay. So how many of those have exactly 0 ones in them? Just 1, right? And here we have all the 1-bit patterns. There are 3 of those, right? And how many 2-bit patterns do we have? We have 1, 2, 3. Happens also to be 3. And we have just 1 3-bit pattern. So in general, we have 3 over L. So 3 choose L. Okay. So the probability that the error pattern has exactly L bits in it is equal to this. And now when we have that, we can actually calculate then what the error, the probability for different types of errors are on the channel. Okay, so you would do you will practice this a little bit at the exercises. So I'll leave some of those problems to the exercises here. So please go to the exercises. If you think this was a little bit strange, and it is the first time you see it, get some getting used to it. Please take the time to go to the exercise sessions and do these calculations. It will save you a lot of time later on if you want to do this on your own. I can almost guarantee you that. Okay, so now let's talk a little bit about practical codes, and we will talk about 3 types of codes here today. And the simplest one, but also actually quite used in practice, is something called single parity check codes. Okay, and single parity check codes use a single parity bit. Sounds reasonable, right? And how do we do that? Well, it's a systematic code in the sense that there is only one parity bit, and that is the modulo 2 sum of all the information bits. So this means that the parity bit is equal to 1 as long as there is an odd number of 1s in D, and it's 0 when there is an even number of 1s in D. So the code word, which consists of B0, B1 up to P0 here, always have an even number of 1s. Okay, so if we then take modulo 2 addition of all the bits in the code word, we have B0 plus B1 plus up to K minus 1, and then plus P0 here. But the first part here is actually equal to P0. So we have P0 plus P0, which is then 0. Okay. So to check whether we have a valid code word, we just count the number of 1s in the received pattern. If that happens to be an even number, we have a code word. If it happens to have an uneven number, we don't have a code word. So the minimum distance of this is 2. We need to flip 2 bits in the code word in order to get a new code word. Okay, so we have an even number of 1s. If we flip 1 position, we get an odd number of 1s. If we flip 1 position again, we might get an even number of bits. Right? So the minimum distance is 2, which means that the single parity check code can find all single errors in the code word. So single bit errors are defectable. However, we can actually detect many more error patterns, namely those who have an odd weight. So if we flip an odd number of positions, then we will be able to detect those errors. So even with a single parity bit, we can detect half of all possible error patterns. So it's actually not so bad. And we can detect all single errors. However, double errors, we're screwed. And all even number of, all error patterns with an even number of 1s in it, we're also screwed. Okay, so sometimes we want to do better. And the next step in okay, so why would we ever use this? When would this be a good choice to use this? First of all, it's extremely simple, right? Simple calculations, just modulo 2 addition of all the bits. So it's very low complex encoding and decoding of this. Low complexity, we love it, right? That's good, it's cheap, right? And then it can fix all single bit errors. So if the likelihood of having double errors is extremely small, then this might be good enough. right? So it's good when we are strapped for resources, when we want to have something which is really low complex implementation, and when the channel is fairly good, in the sense that it's not very often we get more than 1 bit error. Okay, then this is a good code. So these are quite used in practice, right? In memories and things like that. When you store memory, you store the data plus a parity check, right? So when you read off the memory, and then you can have a read error, and you can detect that easily. Okay, the next level of complexity comes when we want a little bit more of detection capability, but we are still concerned about complexity. So then people have been looking at this for some time, and in the late 60s and the beginning of the 70s, one needed some type of error detection capability for TCP, UDP, and IP. Okay, and then these computers one had at those days were not very powerful, right? So one really wanted to find a good balance between complexity, but still a little bit better than single parity check codes. So then one started to do something which is called now a checksum or the internet checksum. So this one is used for error detection in TCP, UDP, and also in IP version 4 headers. And the idea as follows is that it works on any blocks of bits of any length k, and it's like 3 simple things we do. First of all, we take the data and we split that into 2-byte blocks. Okay, so let's now think that we have an even number of bytes here, and each 2-byte block is then 16 bits. Every byte is 8-bit. Okay, 16 bits block. So we split the whole message, into 2 bytes, 2 bytes, 2 bytes, etc. If we have an odd number of bytes to start with, we just put in a 0 byte at the end. Okay. Then what we do is that we take each of these individual blocks, these are 16 bits, and we treat them as 16-bit integers, and we just add them together. Okay. But we add them using one's complement additions. I'll show you on the next slide what that is. But essentially we add them together. And then the sum becomes the parity bits. Or rather, what we do is that we add all the information bytes, and then we get a 16-bit number, as we will see on the next slide, and then we flip all those bits, so we negate them. Okay. And that is the parity bits. And if we do that, if we go through the same process now, but we also append p at the end of these calculations, then at the end of the day we will get a parity pattern which is 0, all zeros. So we can check whether we have a correct p by just repeating the encoding process, and if we get the all 0 pattern at the end, we are happy. Okay, then we accept this as error-free. Okay, so this plus with the apostrophe here, that means one's complement addition. So what is that? Well, it's maybe rarely used nowadays, but that in the days it was easy to do this with the computers one had. And essentially it's like the following. It's like regular n-bit addition, but with something called the end-around carry. Okay, if we had it in decimal notation, so here we have a 16-bit number and 16-bit numbers, regular integers, we can just add them together using one's complement, and that's equal to the regular addition of these two numbers if the sum is less than 2 to the power of n. Okay, and that's because we have n bits. The result should be an n-bit pattern. So as long as it's okay that the sum is confined to n bits, that's fine, we leave it alone. However, if the sum is larger than 2 to the power, larger or equal to the 2 power of n, we need to convert this long, then we need actually n plus 1 bits in order to represent this, and we wrap that together into a 16-bit number. And what we do is we take the sum and then subtract off this number, and then it happens to be a 16-bit number again. Okay. Another way to see this, if we do this in order binary addition, we do this end around carry trick. So if we have 8-bit integers here now, just to keep the number of bits relatively small, the number 225 in decimal, or E1 in hexadecimal, or 11100001 in binary. So this is one number, and this is some other number. If we want to add them together using 1's complement, we can either do it in binary form, and if we have it like this, it's simple. 1 plus 1, it's 0 plus a carry. And then it's 1 plus 1, that's 0 plus a carry. 1 plus 0 is 1. 0 plus 1 is 1. 0 plus 1 is 1. 1 plus 0 is 1. 1 plus 0 is 1. 1 plus 1 is 0, and then 1 as the last carry here. So the blue carry here falls off the edge, right? Because here we have already 8 bits, and here we get the 9th one. That's not good. We still need to have the sum as being 8 bits. So what do we do then? Well, let's just stick it in here, and then add everything together, and then we get a 8-bit pattern. Okay, so this is called the end around carry. The carry that falls out here, we put that in here. If you're used to doing this in binary, I don't know what your preference is. If you're good at binary addition, you do it there. If you're good at hexadecimal addition, you do it in hexadecimal form. You still have a carry here. And then the result of this is 7C, and then you just put the 1 here, and we add that together, we get 7D. So that's 7D is actually exactly this bit pattern. If we want to do this in a decimal form, we have 225 plus 155, that's 380. Okay, and 380 is more than 256. Right? So it's a 9-bit, it's not an 8-bit number. However, if we subtract off 255, we get 125, which is possible to represent with 8 bits. And 125 is actually equal to 7D, which is equal to this bit pattern. So it works. Okay, so that's the internet checksum. That's used on your, whenever you transmit a TCP packet, somebody's going to calculate this for you, right? So next time we meet, we will talk about the next level of complexity, and therefore also the next level of performance. And these are known as the cyclic redundancy code, CRC codes. But let's talk about that on Thursday. And on Thursday, it's 8 o'clock. Yes, I know. See you then. Knäppa av den istället.